Let's think about the most extreme object in the entire universe, a black hole. It's a place where space-time itself has been so warped that nothing, not even light, can ever get out. Now, for decades, we had this comforting idea about them. A promise, really, that was made by our most trusted theory of gravity. We were told that if a black hole was big enough, you could fall right across its edge, the event horizon, and you wouldn't feel a thing. It would just be a quiet, serene drift across some invisible line. But what if that promise was a lie? What happens when our two greatest theories of reality declare war on each other, right at that boundary? A war so violent it could ignite a firewall, a wall of pure energy that would incinerate not just an unlucky astronaut, but our entire picture of the cosmos. Today, we are going to journey right to that edge, to confront a paradox that threatens to set fire to physics itself.
You hear that? For the longest time, the journey was supposed to be a quiet one, a gentle passage into the great unknown. The very laws of physics seemed to guarantee it. But a deep and frankly terrifying conflict at the very heart of modern science, well, it suggests something else entirely. It suggests that at the edge of a black hole, you wouldn't find a silent gateway. You'd find a raging, impenetrable wall of fire. Now, this is not just some sci-fi fantasy. It's a conclusion that we are being forced to consider by the very mathematics we've trusted for a century. So, to really understand how we got to this unbelievable place, we have to start with that beautiful promise, the one that was broken.
So before we can even begin to build this wall of fire, we have to understand the promise that it breaks. This was a promise made over 100 years ago by Albert Einstein himself, a promise of a smooth, completely uneventful journey into the abyss.
According to Einstein's general theory of relativity, the event horizon isn't a physical thing. It's not a wall, it's not a membrane, it's just a location in spacetime, a point of no return. Here's an analogy. Imagine a huge, wide, slow-moving river that flows toward a massive waterfall. Far upstream, you can paddle around, you can go wherever you want. But as you drift downstream, the current gets a little stronger and a little stronger. The event horizon is like that one point in the river where the current becomes so powerful that even the fastest boat in the world can't escape being pulled over the edge. Now, for a truly giant, supermassive black hole, the kind that live in the hearts of galaxies, this cosmic river is incredibly wide, and the current builds up so gradually you wouldn't even notice. The actual curvature of spacetime at the horizon is surprisingly gentle. So the theory predicts that an astronaut, we'll call her Alice, in her spaceship with the engines off, just in free fall, she could sail right across that line and be completely unaware that her fate was sealed. There'd be no jolt, no flash of light, no alarm bells, nothing. To her, it would feel like just another Tuesday in empty space, right up until the moment she passed the point of no return.
This idea, which sounds so strange, is actually built on what Einstein called his happiest thought. It's the equivalence principle. And what it says is that in your own little local patch of space, you can't tell the difference between gravity and acceleration. Think about it. If you were in an elevator with no windows, way out in deep space, and it started accelerating upwards, you'd feel yourself being pressed against the floor. It would feel exactly like the force of gravity holding you on Earth. You couldn't run an experiment inside that box to tell the difference. Now let's flip it. Imagine you're in that same elevator on Earth and the cable snaps. You'd go into free fall. For those terrifying few seconds, you and everything else in the elevator would float, weightless. That feeling, that perfect weightlessness, is indistinguishable from floating in the vacuum of space, far away from any planet or star. This isn't just a fun fact. This principle is the absolute bedrock of general relativity. It's been tested again and again, and it tells us that physics in any small, freely falling laboratory should be simple, normal, and predictable.
And this is the absolute key to the whole promise. Because of the equivalence principle, Alice, as she's falling freely toward the black hole, should feel nothing special at the event horizon. Her local patch of space-time should look, feel, and act just like any other boring patch of empty space anywhere in the universe. The laws of physics inside her spaceship should be completely normal. So, the very existence of some violent, dramatic event at the horizon, like a wall of fire, would be like a giant cosmic alarm bell screaming, "Warning, you are at a black hole." That would catastrophically violate this sacred principle. So, for decades, this was the accepted picture. A gentle, silent, drama-free fall into darkness. A promise we thought was unbreakable.
But here's the thing. General relativity isn't our only tool for describing the universe. There's another pillar of modern physics, an equally powerful and successful one. And when you bring its bizarre rules to the edge of a black hole, Einstein's happy thought transforms into an absolute nightmare. So, on one side of the ring, you've got general relativity. Its champion is the equivalence principle, demanding that the horizon be smooth, local, and utterly unremarkable.
On the other side, you've got quantum mechanics. Its champion is an equally sacred principle called unitarity. Unitarity is the ironclad, non-negotiable law that quantum information can never, ever be truly lost or destroyed. Now, when we say information, we mean the complete, detailed description of a physical system. Every particle's position, spin, momentum, everything. Unitarity says you can scramble that information. You can hide it, you can make it incredibly hard to read, but the universe must always keep a perfect record of what was. It's the law that makes the universe predictable. It ensures that cause leads to effect. These two theories, they are the twin titans of physics. They've both been tested to unimaginable precision and have never failed. But at the event horizon of a black hole, they enter a fight to the death.
And this fight truly kicks off with a revolutionary discovery by Stephen Hawking. He did something no one had dared to do before. He tried to mix the strange rules of quantum mechanics with the warped spacetime just outside a black hole. And the answer he found, well, it changed everything.
What Hawking discovered is that black holes are not truly black. See, according to quantum mechanics, even the vacuum of empty space isn't really empty. It's fizzing with virtual particles that pop into existence as a particle-antiparticle pair, exist for a tiny fraction of a second, and then annihilate each other. Usually this has no effect, but right at the edge of an event horizon, things can get weird. Occasionally, a pair will pop into existence, and one partner will fall into the black hole while the other one escapes. From the perspective of someone far away, it looks like the black hole just spat out a particle. This steady trickle of particles is now known as Hawking radiation, and it has a profound consequence. This radiation carries energy away from the black hole, and thanks to Einstein's famous equation, E=mc², if it's losing energy, it must also be losing mass. Over truly unimaginable timescales, trillions upon trillions of years, this means a black hole will slowly but surely radiate itself away, until it evaporates into nothing at all.
And that leads to a devastating question. Think about everything that fell into the black hole during its long life. Stars, planets, dust clouds, maybe a copy of your favorite book. All of that stuff is made of unique quantum information that describes it perfectly. So, if the black hole eventually evaporates completely, disappearing into a featureless cloud of random thermal radiation, where did all of that specific, detailed information go? Suddenly, we are faced with two options, and both of them seem completely impossible. Both of them seem to break the fundamental laws of physics.
Okay, let's look at the choices. Option 1. The information is just gone. Poof. Erased from the universe forever. This is a direct, violent violation of unitarity, that bedrock principle of quantum mechanics we just talked about. So physicists really don't like this. That leads to the other possibility. The information must somehow get out, encoded in the outgoing Hawking radiation. But that leads to option 2. If the information gets out in the radiation, but a copy of it also still exists inside the black hole, which it has to for Alice to have her smooth journey, then we have perfectly cloned quantum information. And that is strictly forbidden by another quantum law called the no-cloning theorem. You simply cannot create an independent, identical copy of an unknown quantum state. It's a fundamental catch-22. Either information is lost or it's illegally copied. Either way, quantum mechanics breaks down.
For a long time, it seemed like there was a really clever way out of this mess. It was an idea put forward by physicists Leonard Susskind and Gerard 't Hooft, and they called it black hole complementarity. The argument was beautifully simple, almost a philosophical sidestep. The idea was that maybe the paradox is just a problem of perspective. Imagine there are two observers. There's Bob, who stays safely outside the black hole. He could, in principle, wait for billions of years, carefully collecting every single particle of Hawking radiation until he has enough data to reconstruct the information from that book that fell in. But by the time he's done that, the original book inside is long, long gone, crushed out of existence at the singularity. Now think about our astronaut Alice. She's falling in. She can see the original book right there with her. But she's trapped. She can never, ever send a message out to Bob to say, "Hey, Bob, I've got the original right here." Their two viewpoints are completely cut off from each other. So the argument goes, since no single observer could ever, in any conceivable experiment, confirm that both copies of the information exist at the same time, the contradiction is never actually witnessed. And if it can't be witnessed, maybe there's no paradox to solve after all.
And you know what? This was an incredibly elegant, almost Zen-like solution. It put the limits of our own observation at the heart of the answer. For many, many years, the physics community kind of breathed a collective sigh of relief. The information paradox seemed to be resolved. But it turns out reality is a lot more subtle. And a deeper, stranger aspect of quantum mechanics was lurking just beneath the surface, about to tear this beautiful picture to shreds.
The key that unlocks this deeper problem, the thing that shows why complementarity ultimately fails, lies in one of the most famous, most bizarre, and most powerful features of the quantum world: entanglement.
Quantum entanglement is what Einstein famously and dismissively called spooky action at a distance. It's this profound, unbreakable link between two or more particles. Imagine you have a pair of gloves. One is left-handed, one is right-handed. You put them into two identical sealed boxes. You keep one, and you mail the other one to a friend on the other side of the galaxy. Now, before you open your box, all you know is that there's a 50-50 chance of it containing a left or a right glove. But the very instant you open your box and see a left-handed glove, you know instantly, faster than light could ever travel, that your friend's box contains the right-handed one. Their fates are linked. Their properties are perfectly correlated. This isn't just a weird party trick. This is a fundamental way that quantum information is woven together throughout the universe.
Now, this idea of entanglement goes so much deeper than we can even really imagine. Some physicists now have this radical idea that entanglement isn't just something that happens in spacetime. It might be the very thing that creates spacetime. The theory is that the smooth, continuous reality we all experience is an emergent property, that it's stitched together by this unimaginably vast and complex web of entanglement between all the neighboring quantum fields. So breaking that entanglement isn't a small thing. It's like taking a pair of scissors and snipping the very threads that hold the fabric of reality together. Just keep that image in your mind because it is the absolute key to understanding the firewall.
Okay, to see how this web of entanglement breaks everything, we need to fast forward in the life of our black hole. We need to go to a very specific moment in time, a moment calculated by a physicist named Don Page, which is now called the Page time. This is roughly the halfway point in the black hole's long evaporation. It's the moment when about half of its original mass has been radiated away. Now, calculations show that if information is going to be preserved, this is the critical turning point. Before the Page time, the Hawking radiation can be mostly random thermal noise, but after the Page time, the black hole has radiated so much that, in order to not lose information, any new radiation that comes out must be highly entangled with all the radiation that has already escaped. This is the moment when the universe demands that the information has to start coming out in a way that we could, in principle, recover.
All right, let's set up the thought experiment that destroyed the complementarity picture. Let's imagine our black hole is old. It is past the Page time. Now, a brand new particle of Hawking radiation, let's call it particle B, is about to be created right at the edge of the event horizon, ready to escape. Now, we are going to demand that two perfectly reasonable things, be true at the same time. First, we're going to demand that unitarity is true, that quantum information is preserved. For that to be true, our new particle B must be entangled with all the previous Hawking radiation that's already escaped. We'll call that huge collection of particles System A. That's how particle B carries information out. But there's a second, equally important demand we have to make. Here's the impossible situation. Requirement number 1. In order to preserve Einstein's equivalence principle, in order for our falling astronaut to experience a smooth, drama-free horizon, that escaping particle B must be entangled with a partner particle, particle C, that is falling into the black hole. This entanglement across the horizon is what stitches space-time together. It's what makes the vacuum look and feel like a normal, empty vacuum. But now, look at requirement number 2. In order to preserve unitarity, to save information from being lost forever, that same particle B must also be entangled with all the early radiation, System A, which is now light years away from the black hole.
Do you see the problem? Our poor little particle B is being asked to do something impossible. It needs to be fully entangled with its partner C on the inside of the black hole just to keep spacetime from ripping apart. And, at the same time, it needs to be fully entangled with System A, all the radiation on the outside, in order to carry information away. It has become, as a physicist who figured this out famously put it, promiscuous in its entanglement. And quantum mechanics, well, it has a very, very strict rule about that.
That rule is called the monogamy of entanglement. It's a fundamental theorem of quantum mechanics. It states that if one particle is maximally entangled with another particle, it cannot have any entanglement left over to share with anything else, period. It's deeply connected to the no-cloning theorem. You simply can't have one particle whose information is perfectly mirrored in two separate independent systems. But that is precisely what our situation demands. The smooth spacetime of general relativity and the information preservation of quantum mechanics have backed particle B into a corner, forcing it into a state that is fundamentally illegal in the quantum world.
So something has to give. One of these entanglement bonds has to be broken. And the consequences of breaking one of them are, well, they're explosive.
We are at a total impasse. We cannot violate the monogamy of entanglement. That would be like violating quantum mechanics itself. So we're forced into a choice. Do we break the bond between our escaping particle B and all the old radiation, system A? Well, if we do that, information is lost, and we are right back where we started, with the information paradox unsolved. So the only other option is to break the bond that connects the inside of the black hole to the outside. What is the price for snipping that particular thread in the fabric of spacetime?
The price is energy, a truly spectacular amount of energy. You see, breaking a quantum entanglement bond isn't a gentle or subtle thing to do. It releases energy. And when you sit down and calculate the energy required to sever all the countless entanglement links that have to exist across the entire surface of a black hole's event horizon, the result is just staggering. It's a bomb of cosmic scale.
See, in order for every single particle of Hawking radiation to escape without violating monogamy, the universe has to sever its entanglement with its partner on the inside. And when you do that for every particle, all over the surface of the black hole, continuously for billions and billions of years, you create a shell, a screen of incredibly high-energy particles sitting right at the exact location where that smooth, empty event horizon was supposed to be.
And this is the firewall. And let's be very clear. This isn't some warm, gentle barrier. This is a surface of energy so unbelievably intense that anything, and I mean anything, that tries to cross it, our astronaut Alice, her spaceship, a single atom, would be instantly vaporized, completely thermalized into a superheated plasma of its fundamental components. There is no journey into the black hole. There is only instant annihilation at its edge.
So here's the crucial trade-off. The firewall, as violent as it is, solves the quantum problem. It preserves the monogamy of entanglement, and by preventing anything from ever actually falling in, it neatly gets around the whole information paradox. Unitarity is saved. Quantum mechanics is safe. But what about Einstein's happiest thought? An infalling observer who was promised empty space would instead fly headfirst into a literal wall of fire. This isn't just a subtle violation of the equivalence principle, it is a complete and utter demolition of it.
This outcome is so violent, so contrary to everything we thought we knew about gravity, that many physicists absolutely despise the idea. And yet, the chain of logic that leads us here is remarkably solid, and it forces us to ask the deepest possible questions about the nature of reality itself.
This refined, more inescapable version of the problem is now formally known as the Am-Pes paradox. It's named after the four physicists who laid it all out in a bombshell 2012 paper: Almahiri, Maroff, Polchinski, and Sully. Now, their main point wasn't necessarily to prove that firewalls must exist. It was to show with painful clarity that the information paradox was far from solved. They demonstrated that three of our most basic beliefs about the universe: number 1, the equivalence principle is correct; number 2, unitarity is correct; and number 3, our theories work in low-energy situations, are mutually exclusive. You cannot have all three of them be true at the event horizon. At least one of our most cherished principles has to be wrong.
And this table right here, it just lays out that stark, impossible choice. There is no comfortable option. Look at the top row. If you choose to have no firewall, you get to keep general relativity's beautiful, smooth spacetime. You preserve the equivalence principle, but you have to sacrifice quantum mechanics and you are stuck with the information paradox. Now look at the bottom row. If you choose to have a firewall, you save quantum mechanics, you preserve unitarity, but you violently demolish general relativity at the horizon, leading to this brutal, fiery end to spacetime. There appears to be no third way, no path that keeps all our trusted theories in one piece.
Let's just pause for a second on that last phrase, the end of spacetime. This might be the most profound and frankly terrifying implication of the firewall idea. Remember that picture of spacetime being stitched together by entanglement? Well, if you take your scissors and you sever all of the entanglement threads connecting the inside of the black hole to the outside, it's not just that the inside becomes inaccessible. The implication is far more radical. It's that the interior of the black hole may not exist at all. The very space inside might be an illusion that is only created by the entanglement that stitches it to the outside. Without those stitches, spacetime itself may just end. It might just stop right at that wall of fire.
So, is this it? Is this the choice we're stuck with? A paradox on one hand, or a fiery apocalypse on the other?
Well, physicists are a stubborn bunch, and they are exploring other possibilities, all of them just as radical, to try and escape this trap.
And none of these are easy fixes. They all require us to rethink everything. For instance, some ideas from string theory suggest that a black hole isn't mostly empty space with a tiny point at the center. Instead, it's a giant, tangled star-like object called a fuzzball, made of vibrating strings. In that picture, there's no true horizon and no interior, so the paradox just vanishes. Other physicists suggest that our current theories just aren't good enough, that they break down at the horizon and we'll only understand what really happens when we have a complete theory of cosmology. And then there's the most mind-bending idea of all, that spacetime itself isn't fundamental. Maybe spacetime is just an emergent property, like the wetness of water, that arises from a deeper, purely quantum reality based on entanglement. From this point of view, the paradox is just a symptom of us asking the wrong questions about a reality we just don't understand yet.
In the end, this whole paradox, as frustrating and confusing as it is, it's also a tremendous gift. The firewall isn't just a bug in our equations, it's a giant flashing neon sign pointing us toward a deeper level of reality. You see, in the history of science, the places where our best theories break down and contradict each other, those are always the most fertile places for new discoveries. This inconsistency, revealed at the edge of a black hole, is seen by many physicists as the most promising clue we have that will lead us to a final, unified theory of quantum gravity.
And so, this is where we're left, at the absolute edge of our knowledge. We started this journey with Einstein's happy thought, a peaceful fall into darkness. We end it staring at the possibility of a wall of fire, or maybe even the complete dissolution of space and time as we know it. This paradox forces us to question everything we thought was solid: the nature of information, the structure of the vacuum, and the very existence of space-time itself. It's demanding a revolution in how we think. So the final question isn't really about what happens when you fall into a black hole. It's about the very fabric of our own reality. What if this smooth, continuous stage, this thing we call space-time, on which the entire play of the universe unfolds, what if it isn't really there at all? What if it's just a shadow cast by some deeper, stranger reality